Okay, so our discussion this morning is about uh, applying the chi-square. No, not chi-square rather, but the friend distribution or the F distribution, which is the one-way ANOVA. One-way ANOVA is another statistical test, which is equivalent to analysis of variances. So we are going to look at the significant difference among variable. We call the independent variables the factors, and then the dependent variable is the other one. Now, the good thing about ANOVA is that it seeks or it is used to analyze data with more than three variables involved. For t-test, it's only limited up to two means, comparing two means of coming from different sample of different population. But for ANOVA, it can consider more than two or more variables involved. So that is one way ANOVA. Um, there are several things that we're going to look into and doing ANOVA. First, of course, we would like to find out the degree of freedom as to help us find the what we call this one, to find us the result for our F critical, and then at the same time we will also use the we will solve for the actual F value or the F computed, and then we will do the statistical analysis following the 6 steps in performing null hypothesis testing. Okay, so with that saying, those were our objective for this day's lesson. Let's start with identifying the degree of freedom. Again, degree of freedom is really important because we need to have all the necessary. I mean, this is quite different, so they're different from the rest of our degree of freedom because in this case, for ANOVA, there are two degrees of freedom that we are going to consider. The degree of freedom within group, between group at the same time. So first is we will identify the degree of freedom. I mentioned that for the degree of freedom for F the for used for the F critical or the critical value for the F distribution, we have the degree of freedom between, and at the same time we have the degree of freedom within. Degree of freedom between groups and then degree of freedom within groups. Now we have to understand in that in this case we are comparing three or more groups, and at the same time we are comparing it among themselves. Okay? So that's why we have two degree of freedom. If you are seeing now the table, the critical value for the F distribution, there is degree of freedom numerator, degree of freedom denominator. The first column is the degree of freedom for the denominator, and then the degree of freedom for the numerator is your first row. So with that saying, how do we compute for our degree of freedom in between? Degree of freedom, by the way, between is the degree of freedom numerator from the table, and then the degree of freedom between is the degree of freedom df denominator. Okay? Take note of that. For the degree of freedom between, our formula is k minus 1. K minus 1, where k here is our um, number of groups. Number of groups or number of samples. How many, I don't know, how many group samples are there? Okay? That's the K. For example, you are referring to like three or four variables involved. That is our K. And then when it comes to degree of freedom within, that's n sub t minus k. Now, don't be confused. Of course, the k here is the same number of groups, while the n sub k, n sub t is the total number of samples involved in all the groups. So it's like the grand total, the number of samples all in all, including all the groups. If there are four groups, how many samples in group 1, 2, 3, and 4? We add all them together. That's n sub t. Okay? For example, we have group 1 in the test, group 2, group 3. For group 1, our sample size for group 1 is, let's say, 10. Sample size for group 2 is 9. Sample size of group 3 is 8. You notice For ANOVA test, it does not require to have always an equal number of samples in each group. We can still perform ANOVA, even if the sample sizes are not equal. So with that saying, example, our group 1 is 10, 9, and 8, respectively. To solve for the degree of freedom between, it's simply how many groups were there? We have group 1, 2, 3. There are 3 groups, so that's 3 minus 1, which is 2. That's the DF between. Well, the DF in between, that's basically N sub T minus K. N sub T is simply we just have to add the all the respondents from group 1 up to group 3. So we have 19, we have 27, so that's 27 minus how many groups? There are 3 groups all in all, so that's minus 3. That will give us now 24 as our sample. Our NF, our degree of freedom within. Okay? So that's how we use the degree of freedom within and the degree of freedom between. We will now apply the degree of freedom in identifying our critical values. For our critical values, we will use the table. For example, our DF between is 2, like what we have earlier, and then our DF within is, let's say, it's 24. Let's find our F critical. For the F crit, of course, we'll always consider our alpha. Let's say our alpha is 5. Now you use your table. Look for the table, the critical value for F distribution at 5% level of significance. Are you seeing now, or are you on this particular table? F critical for critical value for the F distribution for 5% level of significance. This is the numerator. This is the denominator. Look for the value. Okay, that is 3.40. So this is now our point of comparison where we will compare our computed F later on, whether our decision is to reject or accept the null hypothesis. Still, the same decision. If our computed value is greater than our critical value, then we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. So that's how we are going to do it. Let's say, for example, our DF between is 7, and then our DF within is 32. What is our F critical? Oh, we don't have 32. Let's change this to 30. We don't have 32.
3.30, sir. It's 8:30, yeah.
2.33, sir.
Ah,
2.33 is our critical value. In the event that our DF is between and then within are already beyond 120, which is outside the table, then we will just simply consider our alpha. You notice that the highest possible value for our degree of for our F critical is only up until 1. So it is approaching to 1. You notice the last value there for our alpha. I mean, for the infinite DF degree of freedom between and the infinite value for the infinite value of degree of freedom within, they all, I mean, the result is 1. That is where the value is approaching. Okay, so we have this idea. We know already how to read the table. Let's now have the actual computation for our degree or our critical value. Okay, for our critical value is simply, okay, so our computation for our F value is simply F is equal to MS between, and then we have MS within. Okay, this is our formula. This is mean squared between groups and then the mean squared within groups. But for the mean squared between groups, there is also a specific, there is a formula also on how we solve this one. And then at the same time also for this. Okay? But in the event that our, for example, our given here is of even number sample size, we can simply modify the formula. Okay, we can simplify the formula. Anyway, let's have this one first. For the M, okay, in the event that we have a, for let's start with the MS between. For the MS between, the condition is that this is MS between is simply N, and then the summation of the expression mean for each group minus x bar z squared divided by k minus 1. We can modify the formula this way if this is so, if if all the groups are of same same sample size. Okay, in the event that we have same sample size, then this is how we're going to solve for the MS between. But if different or uneven sample size, not uneven, but different sample size, our MS between is simply the summation of n, and then you have x bars of I minus x bar g squared divided by the degree of freedom between. Remember, k minus 1 is the degree of freedom between, right? As our formula earlier. And then our degree or MS within is simply the summation of n sub I, n sub I minus 1, and then square s sub the square of s sub I divided by the degree of freedom within. So these are our two formula. Now this is only going to, we have it this way, modified this one, only if our groups have same sample size. In the event that our groups have different sizes, then we will use this formula. Okay? Now let's take some example for this. Let's say we have this example. This particular example has this for same sample size. So same sample, for same sample size, you will have x, the mean is an s. So we have 9 x bar placebo, and then you have vitamin C, and then multivitamin. This is 9, 3.5, 7, then 3, 55, 5.5, and then 2.5. So if you look at this, look at the situation here, we have placebo 9, 9. By the way, this is a table of comparing the means for the population of those who took placebo, meaning to say do not have vitamin C intake. Actually, they were just being deceived that they're as if they're taking vitamin C, and then the group who took who is actually taking the actual vitamin C, and then the group who is taking multivitamins wherein vitamin C is in there. Because the comparison made here is that it's like claiming that the number of sick days, the average number of sick days for those who are not taking vitamin C, and those who are taking vitamin C, and even those who are taking multivitamins where vitamin C is in there as well, we're comparing their number of sick days. So this is the standard deviation of their sick days. Then we're making an assumption here whether the number of sick days of these three sample groups actually do not differ from these three population. That's the null hypothesis. And then the alternative is that they simply do not have the same sample. They don't simply have the same mean, all the three population. Okay, the population of those who are not taking vitamin C, the population of who are taking vitamin C only, and then the population who are taking um, multivitamins. So if you look at this, these are just representative for each population. And then we're comparing now their means, whether uh, their mean has a difference, significant difference, or uh, no. Okay? So we will solve first our MS between. Now, with the assumption that we have same sample size, we can now play. Let's start solving F. By the way, in this N here is simply 10. That all three from the placebo group, 10 samples were selected, are randomly selected. And for vitamin C, 10 samples were randomly selected. And then multivitamin also group have 10 samples who were randomly selected. Now, let's start solving our MS between. For the MS between, our formula is that since it's same sample group, it's N, then the summation of x bar I minus x bar G square divided by df between. Df between are simply k minus 1. So with that solving, first is we need to get our grand mean, this one. For the x bar G, that's the grand mean, we will just simply get, since these are coming from the same sample group, okay, I mean same size of sample, then we can just simply get the mean of all the three, add them all together, divided by 3. That's just as simple as that. It's because they just have the same sample size. Otherwise, if not, then we have to select or compute the weight, the mean here, the grand mean, as if we're computing a weighted mean. Okay, which the denominator is still the degree of freedom between. Okay, so let's start. That is 9 plus 7 plus 5.5 divided by 3. 3 because there are 3 groups. That's 9 plus 7 plus 5.5 divided by 3. So we have 7.17. That is our grand mean. Now to solve this one, that's simply our n here is uh, 10. Correct? Our n is 10. It's because we have all the same sample sizes. Okay? So we have it here, this one. And then we will solve this. First is, sorry, it is 10. And then our first mean is 9 minus the grand mean 7.17 squared. Anyway. I'll just, so that you will not be confused, I'll just introduce one. Let's just actually, there is no difference when we do it this way and we do it the usual one. Let's just do it the same way. I will no longer introduce an alternative. I'll just take up of this alternative. So instead of having this formula, our formula is like this. Still grand mean is needed, but this time it's n. The n here is already including the included in the summation. And then the degree of freedom between group. So what will happen here is that we have n times 9 minus the grand mean 7.17 square plus next, that's 7, the mean of the vitamin C group. Then you have, sorry, this is 10, the sample group size, that is 7 minus 7.17 square, and then plus 10, 5.5 minus 7.17 squared divided by 2. That is how we solve our the mean squared between groups. So let's solve this together. By the way, keep doing it in your calculator. What's the answer for this one? The answer is, so solve this one. What's the result? We have 30.83. I hope you got also the same answer. Okay, now let's have, we have already the M is between. Now let's solve for the M is within. I have to erase this one because I need more space, okay? For the M is between, or M is within, M is W. Simply this is that the summation of n sub I minus 1 s squared sub I divided by the degree of freedom within. So in this case, our n is 10 minus 1. For the placebo group, we have 10 samples minus 1, so that's 9 times the standard deviation is 3.5. We have to square it because we're talking about variance. So that's going to be 3.5 square. And then plus the next group, 10 also, that's 9 times 3 squared plus the last group is still 9. Since they are the same sample size, it's 2.5 squared divided by our degree of freedom here within group is that we have 30 minus the k, which is 3, so that is 27. What is the result? Okay, we have 9.17. Now, since we have already this one, 9.17, what was our degree of freedom within? Uh, the between rather.
30.83.
30.83.
So with that, we
30.83.
will solve now let us solve our f. So we have f const is simply ms between divided by ms within. You will have 30.83 divided by 9.17, approximately, what's the value? 83 divided by 9.17 is, you have 3.36. That is our critical value, I know our computed value. If this is our computed value, what was our critical value earlier? Our F critical. Our F crit is 3.30.
40.
No, no. Our sample size here, third, our n here is 10 per group. So that makes it 30. So that is our degree of freedom between is 2. Our degree of freedom within is 27. So what is 227? What is the critical value? It's 3.35. We look at your table. Now let's compare our critical value and our computed value. What can you say? Okay, we reject null hypothesis
Reject.
because
Reject
comparing
the
this
null.
one, our F computed is greater than our F critical, although it's just a matter of 0.01 decimal value, but still, it makes a difference that our F computed is still greater than our F critical. Thus, we reject the null hypothesis, signifying now that there is statistically there is a significant difference among the three means of the population of the placebo group, vitamin C group, and the multivitamin C and multivitamin group. Okay, that's how we solve for our F critical. Okay, let's have an exercise. Can someone read the problem first for us? Just a volunteer to read the problem. Go ahead.
Me, sir.
Go ahead.
So the 240 students in a large introductory psychology class are scored on an introversion scale that they filled out in class, and then they are divided equally into three groups according to whether they sit near the front, middle, or back of the lecture hall. The means and standard deviations of introversion scores for each group are as follows. Front is 28.7, middle 34.3, back 37.2, and then the 11.2, 12.0, 13.5
That is standard deviation.
standard deviation.
Okay? By the way, class, in the formula later on, if remember in our degree of freedom between, there is n sub I minus 1 times s sub I squared. You don't need to square that one anymore if the given is invariance. Okay?
Yes,
Because
sir.
variance, that's why we square this one because our given is in standard deviation. Remember the square root of our variance is standard deviation. So in other words, to return the variance in standard deviation form, ah, to return the standard deviation in variance form, we just square it. That's why we raise our s sub I into square to have the variance result. But if the given is already in variance again, I'd like to emphasize that one that there is no need for us to square the value because it's already in variance form. But if it is in standard deviation, that's why you need to rewrite it into variance form by raising its value to the second power. Okay? Now let us have, okay, let's start with our DF. DF between and DF within. Give me the answer. Our DF between is our DF between is
2.
what about the DF within? Our DF within is 237. Remember
Why?
our total population is 240 minus 3 groups, that is 240 minus 3. That's why you have 237. We're talking about degree of freedom for within group, which is found by simply n sub t minus k. Your n sub t for each group, I mean, there are 200. It was mentioned already that there were of 240 uh, la, large psychology introductory class. So you have 240 minus 3 because there are 3 groups. So that's why you have 237. So with this, what is our F critical? What is the F critical? That is 3.00. Why? Because our between is 2, but our degree of freedom is already in the alpha. I mean, in the infinite value because it's already beyond 120. That's why we right away assume that 2 versus infinite for the degree of freedom between. That's why our value is 3. I hope everybody were able to follow why the value of our critical is, or the critical value is 3.0. Now next is, we have it already this one. We have the critical value. Let us solve for our, in order for us to solve for our F computed, let us solve first our MS between. What is the MS between? Come on. Everybody take time to solve for MS between and then the MS within. First is you compute your grand total. What's your grand total or your grand mean? Or what's your N?
240.
You read again ng reader the question.
The 240 students in a large introductory psychology class are scored on an introversion scale that they filled out in the class, and they are divided equally into 3 groups.
Stop.
Okay, sir.
What have you noticed?
3 groups, sir.
And then they were equally divided into 3 groups. So that means to say you have 340 divided by 3. That's the N per group. Not also 55 natinga. Your N is 80. Of course, that's 240 divided by 3. The answer here for the MS is 1,493.6. Of course, for the MS between, you just simply, that is, don't forget our formula for this one is simply N, the summation of N, x bar I minus the grand mean squared divided by the degree of freedom between, which gives us 1,493.6. That is the ms between. What about the ms within? What's the answer? That is n1, the summation of n1 minus ni, ends of I minus 1 times the squared of the standard deviation divided by the degree of freedom between. Okay, that's 150.56. So to solve now this one, that is going to be 1,493.6 divided by 150.56. What is the uh, F computed? That is 9.92. Now, with this result here, what is our decision?
Reject.
Okay, we will reject the null hypothesis. If we reject the null hypothesis, what possible type of error are we going to commit?
Type 1 error, sir.
Okay, most likely we are taking the risk of committing type 1 error. Plus, it took you so long to solve this one. I don't know what happened to your calculator. Or somehow you did not arrive at the right answer because you mix up all the variables. Okay, I'll pose here one situation, then we will do the test hypothesis for this one. I will no longer review the 6 steps because we've been doing the 6 steps already. We've been doing it, so we'll just apply it, but this time with another statistical analysis or statistical tool to be applied. Okay? Okay, I'm sending now the new question or the situation. Okay, I need somebody to read this, please. Here is the situation. Go ahead. You can do that for us. Go
A
ahead.
psychologist has hypothesized that the death of a parent, especially before a child is 12 years old, undermines the child's sense of
Undermine.
optimism. Undermines the child's sense of optimism that this deficit is carried into adult life. She further hypothesizes that the loss of both parents before the age of 12 amplifies this effect. To test her hypothesis that psychologists has found for young adults who were orphaned but before the age of 12, five more who lost one parent each before age 12, and for comparison, six young adults with both parents still alive. Each subject was tested with an optimism questionnaire whose possible scores range from 0 to 50. The research hypothesis that parental death during childhood affects optimism later in life can be tested following the 6 steps of hypothesis testing that you have already learned.
Okay. So we will perform now. But first is, of course, we all know that the first step is we will state the null hypothesis or we'll um, state the hypothesis. So any suggestion or how we're going to set up our hypothesis here?
Same way sa last, sir. First, state the hypothesis katong.
Yeah, that's a step. So any suggestion on how we state the hypothesis? Of course, our step one, our HO. By the way, for Anova, one way Anova test, our HO is just very easy. We will just say that mu1 is equal to mu2 is equal to mu3 is equal to that. That depends upon how many variables is involved. But in our case, since there are only 3 variables, the optimism score of the kids who lost the 4 kids who lost their parents, both parents before age of 12, and then mu2 is the optimism score obtained by the 5 students who lost their parents or who lost one parent before the age of 12, and then 3 is both parents alive. So we will state it this way. But what must be the equivalent statement for this? So we would say now that there is no significant difference between the number of between the there is a significant difference between the mean of the optimism score of students who lost their parents, who lost one, both parents alive, and at least one parent is deceased. So that is your statement. There is no significant difference. So we're saying now that among the three groups, there is no significant difference between their mean. In other words, the mean of the population of those who lost both parents, of those who lost one parent, and of those whose both parents alive has no difference at all. Okay? That is our F sub O. Now, to make it short, for our F sub A, we cannot just simply state that mu1 is not equal to mu2 is not equal to mu3. We cannot state that because the condition does not only suffice that mu1 is not equal to mu. This is quite confusing or misleading. Instead, what we're going to say here is that there is no no or we say that the mean of the groups are not the same. We will say it this way because it's quite clear. This one, mu1 is not equal to mu2. It follows also that mu1 must not be equal to mu2. Even if an instance happened, like for example, if mu1 happens to be equal to mu3, still it doesn't suffice the idea that equality happens for all the three. So it's like all the three must be the same, even if one fails here. So we better state it in word form that the means of the three groups or the means of the sample groups were actually not the same. That is our alternative. Meaning to say, in this situation here, for the number, for the, there is a significant difference between the optimism score of those who lost parents. Both parents died before 12 years old. One parent die, one parent or a parent dies before 12 years old and both parents alive. So that is our alternative vote. Okay? So we can write the statement this way, implying this one, because somehow this is quite confusing to look at. What's the second step?
Decide, sir, the test statistics.
Okay, so because we want to draw an inference, okay, we tested, we would like to make a conclusion, we would like to infer on something that is comparing two or more population mean simultaneously meaning to say at the same time, together at the same time. So that's why we cannot perform t-test here because we're comparing three um, population mean simultaneously. So that we are going to use, of course, our one-way Anova. But at the same time, we will also assign our alpha. And in this case, our alpha will be 0.05. So we have already assigned our test hypothesis, and at the same time, we also have already assigned our alpha. What is the third step?
Select and collect the data.
Okay, so I'll just make here both dead, one is dead. Just try to understand the table and then both alive. Then we will get their results. So for both dead, the four students who were found was actually having an optimism score of 29, 35, 26, and then 22. And then for both dead, 31 is 30, the optimism score, 37, 29, 32, and 25. And then for both alive, we have 35 optimism score, 38, 33, 41, 28, 40. Now, this is the data gathered. What we need to do now is we will get the mean and standard deviation for each group. Go ahead. What is the mean for both dead in terms of their optimism score? So that's basically, you just have to add all their scores, then divided by the number of scores there are for both parents dead, deceased, and then that's the mean, and then we'll get the standard deviation. If you're using calculator, you can just input all the scores and then select mean and then select standard deviation. The answer will be provided. I don't know who is using a calculator. Are you using calculator, scientific? Please set your calculator to statistics. Go to mode and then select SD. If you're using a lower version, but for other calculator, I cannot really teach you when I cannot see the calculator. But set your calculators to statistics. And then you input the data, this one, that's 29, and then 35, 26, 22. And then shift variance. X bar is mean, so that is, there you go, the mean is 28. There's this 5.447. 5.477. It's 30.6, that's the mean. 4.393. 4.493. 393. Do you have this same value? Because if you were given a raw data, you have to really compute your own standard deviation. But if you're doing the manual computation, instead of getting the SD, better get the variance right away, because in fact, variance is what is needed here. Plus 35.83 is the standard SD. 35.83. And then shift variance, that is 3. You have 4.88. Or in 3 decimal places, that's 4.875. 4.875. So we have already our data. This is the gathered data. We selected the data set, and then we collected the data. Then this is now our partial and partial of our gathered data. Next step 4 is
The
we
rejection.
will identify the rejection region. Step 4. So we will discuss it one. By the way, before I forget, the null distribution of our ANOVA is actually not normal, the same with what we have last time that we have a bell curve. It's actually skewed to the right. Okay, it's skewed to the right. So it appears to be like this, something like, there's a longer tail here. So our rejection here, what is our F critical? Our F critical is, who can give me the F critical? As we will set up our rejection region. This is the rejection region here beyond the F critical. But we must know the F critical first. Right. Okay, that's 2. And then still our alpha is 0.05 as stated in step 2. And it's just one tail test. So 0.5 is 0.05 is still 0.05 and was not divided into 2. But this time, what is our degree of freedom within? What is the degree of freedom within? It is what?
7.
No. There are 4 here. And then this is 5. This is 6. Add it all minus the number of groups. That's 10, 15 minus 3. There are 3 groups. That is 12. So that's 212 of the critical value of the F distribution for alpha 0.05. What is the value? Okay, we have 3 point, this is our critical value 3.89. As we have already set our rejection region, this is the rejection region, reject here, reject HO. This is equivalent to 0.05%, 0.05 level of significance alpha. Then it appears to be one thing. So if that's the case, by the way, also our F computed, there is no way that we will find F computed here. All the F computed is going there because remember, it is squared. Remember F, MS between and MS within, they are all mean squared. So therefore, there is no such way that our answer becomes negative. So every rejection, all the rejection region falls on the positive area. That's why it's somehow skewed to the right. Okay, now going back to this situation here, 3.89, and then that's the value. We have already said, we have already plotted our rejection region. So, but if our value falls in this area here, it falls on the acceptance. So we will fail to reject the null hypothesis if our computed F landed in this area. Now we're good with this one. Let us solve for our, that's step 5, right? Let's do the computation. Let's start with MS between. What is the MS between? Come on. I need everybody to make a solution. What is the MS between? If I may write our formula, that is um, our N for the first one, how many samples were there in those who lost both pairs? That's 4. What is our grand mean? By the way, the computation for the grand mean here, okay, let's start with the grand mean because the grand mean is different from the one that we have last time. So we have X bar G is simply 4 and then that is 28 plus 5, 30.6 plus 6, 35.83 divided by the N total or the total number of samples, that's 15. Correct? What is your grand mean? Round it to the nearest thousands place, to the decimal places. The answer is
32.
32. Now with that, grand mean, let us solve now our MS between. The MS between is simply so that is 4, then the mean is 28 minus 32 square plus 5, 30.6 minus 32 square plus 6 times 35.83 minus 32 square divided by the degree of freedom between is 2. What is our MS between? Go ahead. 4 times 28 minus 32 square plus 5, 30.6 minus 32 square plus 6, 35.83 minus 32 divided by 2. What's the answer? It is 80.91. That is our M is between. What about our our M is within, which is what's the formula for that? That is for, I don't know, it is n sub I minus 1 times the squared of the standard deviation. So that is 3 because 4 minus 1 is 3 times the standard deviation 5.477 square plus 4, that is times 4.393 squared plus 5 times 4.875 square divided by our degree of freedom within is 12, right? Because that is 15 minus 3. Okay, let's solve. 3 times 5.477 squared plus 4 times 4.393 squared close plus 5 5 times 4.875 square divided by 12. What is your answer?
23.83.
23.83. We have already our MS between and MS. Let's solve for our F computed. F comp is MS between divided by MS within. Our MS between is 80.91 divided by our MS within is 23.83. Approximately, what is our computed? It's
3.40.
80.21,
3.40.
23.83. That's 3.4.
Oh, 3.4.
We have already our step 5 completed. This is already step 5. Where are you? This is step 5. So what must be the step 6? What is the step 6?
Sean.
Make the statistical decision, sir.
Okay, you give me the statistical decision.
Failed to reject.
No, that's not how we state the problem. We have to
I
state the
mean,
whole
the
sentence.
hypothesis. Okay, sir.
Yeah, you give me the complete sentence of our decision. Yeah, I know the answer is we fail to reject the null, but I wanted to have the full sentence of our decision. You must know how to present your decision in full sentence.
Since the F critical of 3.89 is greater than F count of 3.40 at 0.05 alpha significant level, hence we failed to reject the null hypothesis.
That's it. What is so hard with that?
Na hinay akong connection sir sa utok.
Okay, so that's it. Since the T, the F critical, which is 3.89 is greater than the F computed of critical than the F computed, which is 3.40 at 5% level of significance, thus we fail to reject HO, or we fail to reject the null hypothesis. Okay, there you go. There you have it. Since the F critical, which is 3.89, is greater than the F computed, which is 3.40 at 5% level of significance, thus we fail to reject the null hypothesis. Okay, now with that, what is your conclusion? Can somebody formulate a conclusion now based from the given?
Since the null hypothesis was failed to reject at zero point 0.5 level of significance, it implies that statistically there is uh, statistically um, the mean of the groupings are what's it called? Are not the same.
So we may somehow say that since we fail to reject null hypothesis at 5% level of significance, it implies that statistically there is no significant difference between the mean of the was it mean of what's this about the mean of the optimism score of the three groups are not are just the same. There's no significant difference between the mean of the optimism score of those who lost their parents, both parents before the age of 12, those who lost a parent before they reach 12 years old, and for those whose parents are both alive. You know that is how you make conclusion is really important because the statistical test will just be there laid down. But how you're going to formulate now your conclusion based from the result and relating it to the problem, that's already on you. Okay? Again, if I'm gonna say it back, since we failed to reject the null hypothesis at 5% level of significance, it shows that or it implies that there is or statistically there is no significant difference between the mean of the optimism score of those who lost parents between lost both parents before the age of 12, those who lost a parent before they reached 12 years old, and whose parents were both alive before the age of 12. So at least that is your conclusion. So that there is a significant difference between the average optimism score between those who lost both parents, a parent is deceased, and then both parents are alive when it comes to their optimism score, the average of their optimism score. Any question? I'm open now to answer any questions or clarifications. We've finished already the 6 steps and we performed already the 6 steps in conducting null hypothesis testing using statistical treatment of one-way ANOVA, wherein we compare three independent samples. By the way, in this case, what are our independent samples or the factors? And that is the dependent sample, and the dependent variable. Our factor here is basically the dependent is the score. The independent is the type of parents has for the respondent, and then the dependent is the factor is their optimism score, while the independent variable or the factor is the type of parents they have.